Very good evening. So today I'll be covering the linear regression model. I'm Dr. Pankaj from IMS College. So let us first try to understand what exactly the linear regression is all about, and why do we study linear regression, where it is used. Uh, Linear regression is basically a statistical technique which basically tries to establish the relationship between the dependent and independent variables. For example, I can have two variables, suppose height and weight of a person. It may happen that height of a person may also, suppose weight of the person may be dependent on height or vice versa. So one of the variable or a set of variables can be dependent on some set of variables or other variables. So there would be what? Dependent variables, and there would be a set of independent variables. Right. So what we need to do is we need to understand how these independent variables can be grouped together, how they can be used so that we can predict the independent variable, the dependent variable based on your independent variables. Right. That is what we try to establish that relationship, and therefore, since it is named as linear regression, so the relationship should be linear in these dependent and independent variables. So they can be a simple linear regression where we have what one dependent variable and we have what a single independent variable. For example, I was taking example of your height of a person, weight of a person. For example, one of the variables can be dependent, and the other variable can be independent. But the thing is, we have just two variables, right? A single dependent and single independent variable. So that accounts for your simple linear regression. The case could be when we have what we can have two or more independent variables, and based on these two or more independent variables, we want to predict what would be my dependent variables. So that would be the case of your multiple regression, right? This linear regression or the multiple regression basically comes under the category of your supervised learning technique. It performs what? Regression task. Regression means a kind of a projection. It basically does a kind of projection based on certain cases of independent variables. So based on these independent variables, I want to predict something. It is basically a regression task. It is basically a kind of prediction set of dependent variable in terms of the independent variable. So there is some kind of at times students get confused between the regression and the classification, because regression is also a kind of classification. But there's slight difference that we must know. So regression classifications, I told you, they come under the category of or umbrella of your supervised learning algorithm. And both share same concept of utilizing your known data sets, which we normally call what training data sets, to make the predictions. Right? So that is what we do in machine learning, in supervised learning algorithm. We use your training data in order to build up a model, and then we use that model to predict the new variables of the predictions are done. Right? So the main difference between this regression and the classification basically is that the output variable in terms of a prediction model is numerical. That means you always predict or you always do regression on your numerical variable, which is basically a continuous variable. Right? But in case of classification, this prediction would be on categorical value, right? Which can be a discrete value also, right? So that's the basic difference between the regression and the classification. You'll get to understand this with an example. I'll come to that example. Examples like, for example, for regression algorithms, which are very common, linear regression, support vector regression, regression trees, and some examples like logistic regression, which actually creates a lot of confusion. So logistic regression, the word regression is there, but it is not actually the regression model, right? So they are not the regression algorithms. These are basically binary classifiers. Right? So Regression analysis is basically used for the purpose of defining the trends in your data. For example, and based these trends are basically based on your historical data. For example, if I'm running a company, and suppose based on the previous year the based on my previous year financial gains, or the based on what how business has run in the previous year, I just want to forecast based on that 1 year study of the previous, that how my business or how my sales would be going for the next year. So this is basically a prediction. So I want values in terms of, suppose, what would be my sales for next year's specific month. So that prediction or that trend analysis would be done on the basis of your previous data. So that is what the basic purpose of your regression analysis is. Another, like for example, there is what connection between how much you eat and how much you weight, right? So regression analysis can help you quantify that also. So regression analysis basically provide you with a kind of linear equation for a graph, so that you can make a predictions about your data. Like for example, the same example, if we put like if you're putting a lot of weight over the past, suppose 3 years, and if you want to just predict that how much based on what weight I have, what weight in what manner I have gained the weight last 1 year, I just want to predict that if I go with this kind of rate, then what would be my weight say after 10 years, the time to come, right? So this kind of trend analysis, this kind of prediction basically can be done through your regression analysis. So overall, like essentially this regression is basically makes a best guess at using the set of data to make some kind of predictions. So it is basically fitting a set of values in a graph, isn't it? Regression analysis techniques basically predicts what continuous responses. Like for example, it can be the change in temperature, fluctuations in the electricity demands, the sales record. It can be your forecasting of or your the stock rates, right? So all this comes, all these techniques, all these problems are basically solved through these regression techniques. It might include forecasting, as I've told, the forecasting stock prices, handwriting recognition, right? Caustic signal processing. So wherever we need to predict a continuous response in terms of value, the regression techniques can be very useful. Common regression techniques, as I've already covered previously also, it includes your linear and non-linear regression. It would also include your Gaussian process regression model. SDM regression is very popular. Generalized linear model regression tree, and there are many other variations of regression models that are known. In statistics, this regression or linear regression is basically nothing but an approach for modeling the relationship between your dependent variable y and one or more independent variable. We call them as what explanatory variables, right? Which we have already discussed. And we'll be starting with the simple linear regression first, where we have taught we have only what one dependent and one independent variable, right? For more than one explanatory variables, the process, as I've already said, is a multiple linear regression, right? And we normally also call that as what the multivariate linear regression, where the multiple correlated variable, independent variables are predicted, right, rather than a single scalar variable. So when we implement linear regression of some dependent variable y on a set of independent variables, right? For example, we have independent variables can be represented in the form of say x, 1 to xr. So r is what? The number of predictors. So we normally call these independent variables as what? Predictors, right? So what actually the relationship we are talking about, the linear relationship we are talking about, it can be of this form, where y is your what? Dependent variable, and relationship can be of this form, right? So where this equation itself would be called what as regression equation. And these b0, beta 1, beta 0, all these are what? These are regression coefficients. These are the constant values. And we also have one term that is called the random error, that error between your what would be the actual value and what prediction has been done. So there could be always an error between the two, right? What we predict and what is the actual value, right? So that epsilon is basically taken as what your random error, right? So this is how the regression models or the linear regression models would look like, right? Linear regression basically calculates what the estimators of the regression coefficients. Like so we would be actually calculating these coefficients based on what? Based on my training data, right? So we must have a training data where we have what both x and y, that is both your predictors and as well as your the dependent variable, right? So we need to have that data or data set where we have these kind of values, and based on that, so this data set can be basically called as a kind of historical data, right? It can be basically a training data set. So based on this training data set, we would be building a model like this. We would be building a equation, linear equation like this. And once that is done, so what we can do is we can pass upon these new values of x. We can have a new set of data set of x or new values of x which has not been used in the training set, and then we can just fit. So by training we would be getting some kind of values for these regression coefficients, right? So we just need to fit in new values of x, and since we have the regression coefficients available with us, so we can directly apply y and we get the value of the prediction value, right? So that is how the model works. So this model can look into, we can define this model to be in this fashion, right? The function should capture the dependencies between your input and the output sufficiently well. So unless what kind of dependencies are there between your all the x, that is all the independent variables. So this regression coefficients must somehow fit those interdependencies between your x well enough so that this model becomes a better model, right? This estimated or the predicted response we normally call as suppose fxi, that is after applying the function on your all x's, right? So for each observation I is equal to 1 to n should be as close as possible to the corresponding actual response. So therefore, definitely there would be a value which we would be getting after applying this prediction model, that would be called, that we would be start calling it as a predicted value, right? And therefore there would be some actual response also. There would be actual value also, right? So the difference between them should be minimized, and in order to minimize the difference, we need to think in terms of some mathematical analysis also. So this difference y minus of fxi. Fxi is your after applying the model, right? Once we build that model, and yi would be your actual value, the actual response that may exist, right? So the difference between these two quantities would we start calling it as what? Residuals, right? The regression is basically about determining the best predicted weights or the regression coefficients. The If these regression coefficients are predicted in a better way, then we see that the model would be fitting quite enough well, right? So this error, and that could be only the case when we have a smaller values of these residuals. So these error must be minimized, right? And in order to minimize this error, in order to mathematically record this error, what we do is we take the sum of these squared residuals. We often call it as what SSR. So we would start using this word SSR. So you should understand that. So it is nothing but the square of this difference that we were talking about, right? So we need to minimize this difference while trying to understand that how well this model has fit, right? So that is what would be the primary first primary objective of fitting the model. And this approach we would start calling as what? The method of ordinary least square method. Right? So let's understand it more clearly, that how a simple linear regression would look like. So we are basically attempting to fit a model like this, right? So where we have the x is what, a single independent variable, and we have a and b, right? And y is basically what, the y is basically a dependent variable, right? And this a would be the slope, right? I hope everyone understands what slope is, right? And b would be the intercept value. So by training the model, we would be actually fixing the values of a and b, which would be called as constants, right? So these coefficients a and b are derived based on minimizing the sum of your square difference of distance between your data points, right? There must be some data points which we are trying to fit in, right? So the data points and your regression line. So based on this data points, if I say that this is, I have my data points. So what I'm trying to do is I'm trying to fit in a line so that the distance between these data points and this line should be minimized. And we're talking about the square difference, not the only difference, because the difference would be mathematically difficult to handle, right? So we would be making it as a square difference so that it becomes positive, right? So after the building of the model, so we may get equation like this, right? Where we have got the values of a and b, right? So what we can do is we just can provide the new values of x. So the model is ready, and then we can obtain the value of, or we can see the new predicted value, right? So this kind of model that we are trying to build up. So this would be a simple case of linear regression model, right? So over here, you can see that, say for example, slope of 2. If I get a slope of 2, so what it means that every change of 2 units in x will yield 2 units change in y. So that is what it means when we say that we have a slope of 2, right? So this is how a linear regression model might look. And so we have actual response, say the response variables, say suppose yi shown in green, and then we have a predicted response, right? Through the trained model, right? And the estimated regression line, which is shown in your black line as the equation. So we have built up our equation like this: fx is equal to, say, suppose b0 plus of b1x, right? And so the goal is to calculate the optimal values of your predicted b1 and b0, as we have taught, we have just covered, right? That is the slope and your intercept, right? And we have to minimize this SSR value, right? So that is what we would be trying to do while fitting the model, right? So let's take a very simple example so that we understand the mathematics behind it. So for example, I have two variables, taking the case of simple linear regression, right? So I'll consider this, any of the variables can be dependent or any of the variables can be independent. For example, I have an x and y. This x can signify anything. For example, it can signify your weight of a person, y may signify the height of a person, anything. It can be two different marks. For example, x1, xi could be the marks of statistics and y could be marks of suppose mathematics. So I just wanted to understand that if I have been given marks in suppose one subject, right? So how I can predict the marks of suppose, for example, I have been given mathematics marks, right? So I just wanted to make a model like between the marks of mathematics and statistics. I just want to predict if I do well in mathematics. So based on my previous result, or based on my previous results between, or a correlation between your x and y, right? That is between the marks in mathematics and marks in statistics. I just want to understand that in the future, if I know the mathematics marks, so how well I'm going to do in the statistics, or so vice versa, right? So this could be any kind of variable where some kind of correlation uh, must exist, and that correlation has to be linear in nature. So suppose I have been given suppose x and y, right? So mathematically, what we would be doing is we first need to find the mean of these variables x and y, right? So that is what 78 and 77 has been calculated. Then what we have done is we would be calculating this xi minus of x over here is the mean value, right? This x over here is the mean value. This is the mean value, right? And suppose, and similarly this y is also the mean value. So what we have done is for each value of x, I have subtracted it with the mean value, that is 78. So 95 minus of 78 becomes for 70. So I hope that is clear. And similarly, your 85 minus of 77 is 8. So the first that we would be doing is we would be calculating these two terms, and then as we have told that we would be squaring these the differences. So we have done what? We have squared this xi minus of x mean whole square, and similarly by I minus of y whole square, right? And then we have also taken what this is called uh, the multiplication of these two variables, which is basically your, so one of the terms is your covariance. So this is basically the covariance term, right? So we have taken these two terms and we have calculated the sum at the end, right? We have calculated this term, and so what we would be doing is we would be directly fitting into the mathematical model. So there are two terms. So what the model is like, what we are trying to build up is y is equal to suppose b0 plus of b1x, right? One is your slope and one is your intercept, right? So in order to find the slope b1, what we are trying to do is, so this is the formula that we would be fitting in, right? So we have what xi minus of this part we have already calculated over here, right? So we would be dividing it with what, the square of the term xi minus of x mean whole square. That is what we have got. So by dividing, we have what 470 is this term, and then we have what xi minus of x whole square is what here 730. So we have got this value of b1, right? So since we have got the value of b1, so what we can do is, in order to get the b0, so what we can do is, so in order to get the b0, I can just equate this from the equation. I can keep y minus of suppose what b1 x, right? That is what we can do. That is what we have written. This y is the mean value. Remember that, right? So then we have tried to find this value of b0 by putting what y mean is for 77, right? And then we have put what b1, we have already calculated that 0.644 into x mean. X mean is what 78. So that is how we would be obtaining what the value of b0. So this is how we do it mathematically. And when we would be learning the algorithms, this is how the machine learning algorithm of linear regression, simple linear regression would be doing the mathematics behind the scenes in order to fit a model, right? So ultimately what we got is what, two values of suppose b1, another value of suppose b0, right? And that's what we can build up the model. So making this equation basically we call it as what, we have built up a model, right? So last we can do is what, so given some new value of x, right? So given some new value of x, we can just put in into this equation and get the predicted value of y. That is what we wanted to do. We wanted to predict the value of y, which was a dependent variable on x. So x can be provided. This values of coefficient regressions have been found by the training the data. So here the training came from this set of items that we have in terms of x and y, right? So I hope that is clear with how linear regression model works. So like how well my linear regression model has done. So we need to also understand that part also, right? So for that we have something called goodness of fit, right? Which we call it as what R-square method. So R-square is basically nothing but statistical measure to show or to understand that how close the data, how close my data to the fitted regression line. This data is all about what? The data that we are trying to fit. So there must be what actual fit also, which is the actual y, right? The actual response. So you just wanted to see that we need to understand that how well my regression line has fitted into my data. So if there is the error between the actual and the fitted value is less, that is what we wanted to calculate it. And that is what R square actually accounts for. So if, for example, if y is your actual value, right? Actual value is the actual target value, which for a given data, the value y is there, right? So suppose I have some actual value y, and suppose y dash the mean value has been calculated, and suppose yp, that is the predicted value. This predicted value came from what? By fitting the model. We have done the training and we have obtained that model, and that is what py has obtained. Yp has obtained. It is the this value that we have obtained can be termed as what? The yp, right? That is the predicted value of y. We just need to fit it into this in order to calculate this R square. There is 1 minus of yp minus of y whole square. That is the summation. In case we have what? Definitely we can have what? More than one values, right? We can have, we may not have only single value, right? It might be an array also. So by dividing this term, by applying this term, we would be calculating what? R square, right? And this R square technically would mean what? This R square would indicate a better fit, right? Larger values of R square would indicate a better fit. So what we're looking for is the models which have a higher values of R square. It would be in terms of percentages, right? So whatever value we would get, it then it would be converted into percentage, right? For example, if I have the 0.89, so we are talking about 89% of R square, which is pretty good, right? Very good. So this would better explain the variation of your output with your different inputs. And in case suppose R square is equal to 1 would indicate 100%, which is where it actually corresponds to SSR value of 0. That is, it's a perfect match or a perfect fit, sorry. So since the values of predict and the actual responses are completely fitting together, which in real senses are not possible every time. So we'll take a practical example also in order to understand. So in exams, you normally would be given these kind of examples, where you would be given a set of points, suppose x and y, the way we have taken earlier, right? Then what we have to do is, you don't have to calculate the entire the values that we did in the earlier case. So what you need to do is just take the product of these two terms first, right? And also calculate, suppose x square, right? So that is good enough for this particular example, right? And then what we can do is we have a total summation over here. We have a summation of this case, and then we can just put in this formula directly, right? So we have n. N is the number of samples we were talking about, right? And then this term we have already calculated, and we have individually x and y also, summation of x and y, and we can just divide it by what? This term, right? So all these terms are available with your data. So we just need to fit in the values and get the values of, suppose this is how A would be defined, and this is how what the B would be defined. You just need to remember these two formulas, and once you get these values of A and B, right? So we can build a regression line. This is a linear regression line that we built, right? And then once we get these values, we can just have new values of x, and we just can predict the value of y. So this is what a simple linear regression model might look and might work with, right? And similarly, we can have the multiple linear regression models. So the concept would remain same. The only thing this time is what we have more than one independent variables, right? That is, we have more than one predictors, right? In the simple linear regression, we had only one predictor, right? So we have what? Linear relationship. So, but the relationship would remain same. That relationship would remain linear in nature, right? So the independent variables are not too highly correlated with each other. That is what is desired. These independent variables that we would be talking about should not be highly correlated with each other. The more the correlation would be, it would be difficult for a model to be fitted, right? And each of the bias observations are selected independently and randomly from the population. That we would make sure that whatever observations we fitted, where we would take, it would be selected randomly, and it is selected independently of one another. There's interdependence between your the observations would not be there. Right? So the residuals should be normally distributed, right, with a mean of 0 and variance, right? If we want a good result, that is what mathematically we should have. And if there are, suppose, for example, two independent variables, like for example x1, x2. So now the model might look in this fashion. Suppose b0 would be the intercept as usual, and then we have what b1 x1 and b2 x2. This is how the model might look like, right? So this basically, in case of we have what two independent variables, so then we can represent this regression plane in what a three-dimensional space, right? But this is the case only when we have got two independent variables, right? And the goal of any kind of such regression is to determine the values, as we have already discussed. The values over here, what we need to determine is the B0, B1, and B2. It is what we are looking for, and the better these values are found. And when we say this constant b0, b1, and b2 must be well fitted, it means that depends on your training data. The better your training data is, the better the opportunity is for these values to get stabilized. That is b0, b1, b, all these constants, right? So that depends on your training data. So so the case when we have more than two independent variables would be almost a similar kind of scenario, right? The estimated regression function might then look into would look to like where we have what suppose then we have what r plus of one weights where we have to determine when the number of inputs is suppose r, right? So this is how the multiple linear regression model might look like. We have beta 0, beta 1, so these are all regression coefficients, and we have an error as the way we have, this is the residual error we're talking about, and the all these y's would be called the dependent variable, xi's are called what explanatory variables, and then we have already discussed these terms. So I hope you've understood this multiple linear regression. We can have a case of polynomial regression also, like this polynomial regression can be in a case it's a generalized case of linear regression. So we normally assume what we assume the polynomial dependence between the output and the inputs. Like as of now, we were talking about the dependency was in terms of linear only. But in case the dependency is in terms of is in terms of mathematically it is polynomial dependency, then we would be talking about what the polynomial regression, right? So I hope that is clear. In one case, we had what linear dependency among the dependent and independent variables, but over here we are talking about the dependency is in terms of mathematically polynomial dependency, right? So in addition to like the linear terms like b1, x1, so regression for this model we would also include the terms with more than one degree. For example, we can have equations like b2 x1 square, b3 x1 cube, like this, right? So the simplest model might look of a polynomial degree of 2 would be like, say, suppose fx is beta b0 b1x and plus b2x square, right? So this is a very simple model of degree 2. And the more the degree increases, we can elaborate this equation, right? So again, we have to remember that we want to calculate these constants in the same manner, beta 0, b1, b2, all those, and with the objective of minimizing the SSR. And that is what these basically are called what unknowns, which are unknowns. So this is how we can cover what the linear regression as well as, and we can have a variation of suppose polynomial regression. So I hope you were able to understand the basic concepts of linear regression and the polynomial regression. And the next time, the next class, we would be covering the implementation part of these regression models